All right, so we're taking a look at rotational motion now. Here on the left side, we have the equations for translational motion. So you may remember these all the way back from the beginning of the textbook. So the final position is equal to the initial position plus the initial velocity times time, which is like the amount that the object moves due to its initial velocity. And then you have to add in the amount that the object moves due to its acceleration, which is the 1/2 at squared part. The a corresponds only to constant acceleration here. That a has to be a constant in order for this equation to work. The second equation here, so this, let's call this the first equation. The second equation tells you how the velocity changes if you're accelerating. Again, it has to be constant acceleration. So the final velocity is equal to the initial velocity plus the amount that it changes due to the acceleration, which is a times t. Equation 3 here. This equation, we had it all the way at the beginning of the semester, but we could really derive this equation quite easily from the work energy theorem. And that's that the final velocity squared is equal to the initial velocity squared plus twice the acceleration. Again, acceleration has to be constant, times the displacement along those directions there. So if you want, you can make sure that you subscript all of these quantities here. And of course, you could have some equations for y as well. Then what we started doing was replacing these quantities on the left, which are for translation, with their rotational counterparts. So x is a displacement in, along a direction. Theta is a displacement along an angle. Okay, so we replace the translation variable with a rotation variable. So x is going to become theta here. V, the translational velocity, will become the angular velocity, omega. And a, the translational acceleration, will become alpha, the angular acceleration. So we've replaced in this equation for the x position, we've got now the kind of angular position. Theta final equals theta initial plus omega initial t plus 1/2 alpha t squared. So now we're going to go ahead and do the same thing for the second equation here. Let's go ahead and change v to omega. Change v to omega. So omega final is omega initial plus the amount that it changes due to the angular acceleration. So plus alpha t here. Simple as that. Just replace v with omega and a with alpha. In the last equation here, in equation 3, we can do the same thing. So omega final squared is equal to omega initial squared plus twice alpha. And then here we replace x with theta. So it's really delta x in this formula. So we got to put delta theta here. So times the angular change there. Okay. A couple of you still have your hands up, Evelyn and Irving. Are there any questions, or you guys are good? Now let's take a look at why we can do this. We've already seen it in the textbook. I'm sure you guys have read already, but the reason we can do this simple substitution here is because the definitions of these rotational quantities are almost identical to their translational counterparts. So for velocity, we have delta x over delta t, right? Well, for omega, we have angular velocity is equal to delta theta over delta t. And these are your definitions now. These are definitions. So because we define these quantities in a similar light to how we define the translational quantities, then we end up with very similar equations here. So this is a definition. Okay, and the same is true for the translational acceleration here, delta v over delta t here, right? And so that's going to be equal to, or sorry, that's going to be similar to alpha, which is defined as the change in omega over the change in time. Okay. So again, this one is also a definition here. Now, what do we mean by theta, right? That's the only thing we haven't talked about here. We've defined omega, we've defined alpha, but what is theta? Well, let's take a look at theta now. So let me see if I can create a nice little coordinate system here for us. Like this. Right, and whoops. And suppose that we have some object here, like so. Right, and for this coordinate system that we've drawn here, where we have, let's say, x and y axes like this, it's pretty clear that this here is an angle measured with respect to the positive x-axis. We could call this an initial angle, theta sub I, right? And if we were to change our coordinate system, if we were to label x and y in some other way, right, maybe we put x and y at an angle like this, then, theta initial could be some other numerical value. So we understand that position is not, position is arbitrary. It depends on how you define your coordinate system. What really matters is how things change, right? And so if this little mass here, or this little object, were to rotate by some amount over to here, then we could draw, again, another line from the beginning, or sorry, from the origin of the coordinate system to there. Then we could label this angle here as the final angle, theta final, right? And now the quantity delta theta is now a physical quantity. That's theta final minus theta initial. Right? Do you guys remember that discussion all the way back in the first couple chapters? Position is kind of something just based on how you define your coordinate system, right? But a delta x, a displacement, that's a physical, a real thing. And that's why our equations always have deltas in them. Same thing is true here for angular displacement. So delta theta is called angular displacement. I'll go ahead and write that out. Angular displacement. Okay, and I'll fill in the gaps here. There we go. Okay, angular displacement. And that's pretty much everything that we need to kind of just do an example now, and see, kind of just get a little bit of practice with how these equations work here. So let me go ahead and pull up an example. We'll take a look at some motion with constant angular acceleration. Okay, and I have an example right here. So let maybe leave that there for a second so you guys have some time to copy it down. Let me make a little line here. And so we'll go ahead and do an example. I'm going to go ahead and type out the example here. So a centrifuge is accelerated for 30 seconds. It begins at rest and has a final angular velocity of 20,000 RPM. And that's the setup there for the problem. And then part A is what is the average angular acceleration? So I'll just write that as alpha question mark. B asks how many revolutions And then part C asks, oh, actually there is no part C here. So this is the example that we're looking at here. We have a centrifuge. If you don't know what a centrifuge is, let's go ahead and maybe draw a little picture here. So a centrifuge, if you just look at it in a chemistry lab, it's kind of like this thing here. It looks kind of like this, almost like a flying saucer or something. And this thing has a motor in it that's going to spin this thing really fast. And so let me see if I can draw maybe crudely here. What is it called? A test tube that you would put inside the centrifuge here would look like this. And you would have some liquid inside this test tube. And if you spin this thing around really fast, what happens is anything that's in that liquid, that's what we would call a precipitate, would actually be forced out of the liquid as like a powder on the side of the centrifuge. So if something is actually dissolved inside that liquid, then the centrifuge, when it spins up like that really fast, is not going to actually get any of that out. So if it's dissolved in there, it won't come out. But if it's not dissolved, in other words, it's a precipitate, it will come out. And like oftentimes it's some sort of like white powder that builds up on the side of the test tube. Okay. And this thing, as you can see, this is a pretty big rotational speed there, or rotational velocity, or angular velocity. Some of those can be used interchangeably. Okay, so 20,000 rotations per minute. Now, in this particular question, we're being given angular velocity initially, final angular velocity, we're given a time that this thing accelerates, and so we can calculate the angular acceleration from the definition. But how do we calculate the number of revolutions that this thing goes through in that amount of time? Well, revolutions, the number of revolutions is related to the angle theta, or rather the angular displacement delta theta. So one revolution is equal to a delta theta of 2 pi, right? So we'll put 2 pi radians here just so we have the units on both sides. So one revolution is equal to an angular displacement of 2 pi, right? So that makes sense because you just go around in a full circle. A full circle has 2 pi radians, so that's one revolution, right? So I'll go ahead and let you guys calculate. You guys go ahead, I'll give you like a couple minutes here to calculate alpha here and the revolutions. And I'll just be here. I can answer any questions if you guys have any. And I'll go ahead and also write some stuff down as you guys kind of make progress there. So we'll do this question first individually, and then maybe on the next question, I'll put you guys into breakout rooms and you guys will work with at least one other person. Maybe we'll alternate or something like that just to keep things fresh. Once you've calculated an answer, go ahead and put it in chat. And that allows others to check. And I will go ahead and write down some helpful things here. But please don't wait for me to write down how to do the question. Feel free to work ahead.
Do we need to change the seconds to minutes to match the RPM, or does it not matter?
That's a good question. So if you're gonna plug those two things into the same formula, you better convert one of them, to the other units, right? So like you can't have minutes and seconds in the same formula.
Yeah.
So it's up to you which one you want to convert. Um, my recommendation though is to always convert any units of time into units of seconds because that's the SI unit. And a lot of the formulas that we use, we have to have SI units in there. So, for example, in the second equation here for part B that you're going to end up using, alpha is going to be something that you want to have in terms of radians per second squared, right?
Hmm.
You're going to multiply it by t squared. But you could have it in terms of, like radians per minute per second, but it's then you would have to not write it as t squared. You'd have to write it as like t times t, and one of the t's would have to have units of minutes, the other t would have to have units of seconds, and so it just gets really awkward
Hmm.
if they have different units.
Okay. Okay, thank you.
Uh, I'm going to start filling in a little bit more information here. You actually change this. A couple people writing in chat now. That's a good sign. Okay, you've got similar answers there. So everybody else, try to check your answers. See if you agree with their answers or not. So I calculated omega final to be 2094 radians per second. So if you got that, you're probably on the right track there. Just move on to part B once you're done with part A and see if you can get that part. Okay, good. Okay, and so there is the answer there for part A. I'm hoping everybody finished part A before I did, but there it is. If you got a little bit lost in there, first thing to do is kind of convert that final angular velocity that they give you of 20,000 RPM into radians per second, and then use this formula here for alpha, this definition, because you want to get alpha in terms of radians per second squared. You should notice, those of you working on part B here, you should notice that you're free to choose your coordinate system, right? So you can make theta initial 0. The initial angular velocity is also 0 because it begins at rest. And you come up with this formula that maybe you have seen before. And that is that theta is 1/2 alpha t squared. Looks awfully a lot like, x equals 1/2 a t squared, right? So I'll go ahead and keep kind of slowly moving forward, and then hopefully you guys are all ahead of me. Put your answers in chat if you've got the answer for the number of revolutions. I got for the total angular displacement there roughly 31,000 I'll write it as 31.4 times 10 to the third radians. So it looks like it's going to come out to a nice round number here. That is not the that is not going to be your answer for part B though, because that is in units of radians. I want to then convert that answer to revolutions, right? So revolutions is equal to the theta final that we calculated divided by 2 pi. And so yeah, it looks like it's going to come out to 5,000 there. Okay. So let me know if you weren't able to get that answer. Let me know if there's one particular spot where you kind of got stuck. I'm going to talk through the problem real quick, just so we have a good idea of what we need to do when we come across a question like this. So just feel free to stop me if you have a question. So when we're given a problem like this, we first recognize, okay, this is, rotational motion, right? We're told this thing is going to rotate. It's going to start at rest. It's going to rotate up to an angular speed of 20,000 RPM. And it tells us how long it takes for it to accelerate to that angular velocity, 30 seconds. And so we're going to apply our definitions of angular acceleration to calculate the angular acceleration as delta omega over delta t. But we got to be careful with this 20,000 RPM. You always want to convert RPM to radians per second. Always convert RPM to radians per second. I've got that little conversion right here at the top. If you want to remember this formula here at the top, you take RPM, you multiply by 2 pi, and you divide by 60. So the conversion factor is like pi over 30, if you want to remember that, or 2 pi over 60. So you take revolutions per minute, multiply by 2 pi over 60, and that will convert for you. So it's a nice little thing to remember. So 1 RPM is 2 pi over 60 radians per second. Okay? So once you've done that, you've got it in radians per second, then you can go ahead and calculate alpha as delta omega over delta t. Here in this case, the initial omega is 0. The final omega is what we calculated from our conversion of 20,000 RPMs. So 20,000 RPMs is roughly 2,100 radians per second. Divide that number by 30, right? It's this number minus 0, so it's basically this number divided by 30. You get roughly 70 radians per second squared. Then you can go after calculating the total number of revolutions. Don't fall into the trap of putting all of the units in this equation here in terms of revolutions per minute, okay? Don't do that. That's going to lead to a lot of mistakes. Never use RPM in this equation, okay? I can just foresee it now. Somebody trying to use RPM in this equation, just don't do it, okay? It's just not a good idea. Never use RPM for this equation. Always put everything in radians per second. The reason is because this thing has alpha in it and it has t squared in it. That's where you're going to make the mistake. If you just had this right here, if you just had theta and omega in there, you could get away with doing revolutions per minute. But because you have the alpha and the t squared in there, just don't do it. It's just gonna complicate things, and that's where a lot of mistakes are going to be made. Okay, so that's maybe a little bit of a trick you can maybe have under your belt. It's okay to use RPM if it's just theta and omega, but as soon as you have alpha and you have like a t squared, you don't want to use RPM anymore. Okay, once we plug everything into this equation here, again, we get an answer in terms of radians, right? This is radians, not revolutions. So we have to back convert. We have to convert this back into revolutions. And the way you do that is you multiply again by, you divide. 1 RPM is 2 pi over 60, right? So you can convert that to, sorry, no. Back up here. We're looking at revolutions, not revolutions per minute. 1 revolution is 2 pi radians. So we simply take this thing and divide it by 2 pi. It was right there. I just didn't notice it. So to get revolutions right here on the left side, you just take your theta and divide by 2 pi. 2 pi is 1 revolution, right? Okay, so we'll go ahead and go on to the next topic now. Since there were no questions there, unless if somebody does have a question, just let me know. And the next topic here is, actually before we get to torque, it is rolling without slipping. Rolling without slipping. Okay, let's put a capital R here. Now, rolling without slipping means that if you're on a bicycle, let's see if we can get a decent looking picture here. If you're on a bicycle and your wheels, let's just ignore what's going on over here, okay? Maybe it's a car instead of a bicycle, since it's easier to draw. When these wheels are rolling on the ground, if you have rolling without slipping, then there's a relationship between the amount of distance that's traveled. So this is your translational motion. And this here is your rotational motion. And if there's no slipping, then the amount that your tires rotate as you move forward in your car should be related to the distance that you travel here in that direction, right? So if I were to roll the tire on the road, if the tire is rolling, then the tire is moving forward on the roll, right? On the road, sorry. It's a little bit of a tongue twister there. And so if the tire has a circumference of 2 pi times its radius, right? There's a radius r. The circumference of the tire is 2 pi r. Then if the tire goes around in 1 revolution, then the distance that it travels is equal to 2 pi times the radius of the tire. So this is without slipping. So this is the distance traveled in translation. This is the radius of the tire here. Okay. So if you roll without slipping, then there's a nice relationship here between these, for example, between the angular velocity of the tire and the velocity of the car as it moves forward, provided there's no slipping. So if there's no slipping, then that implies we have the following identities here. That the distance traveled, or excuse me, I should be more precise. The displacement in the direction of travel will be given by the angular displacement of the rolling object, the tire, right, times the radius of the tire. And the velocity of translation will be given as the angular velocity of the tire times the radius of the tire. And likewise, the translational acceleration will be given as the angular acceleration times the radius of the tire. Again, this has to do with the fact that if you're rolling without slipping, right, then your tire, the length around your tire has to be equal to the length that you travel in that direction. So every little bit of distance that I travel, and maybe I can try and highlight that here for you guys. So this distance here, if I travel this much distance, then I must have had my tire roll through an amount of distance, which when I unravel it is exactly equal to this distance here. Right? So only without slipping is that going to happen, right? If I have slipping, well, then there's no relationship between these quantities here. There's just no relationship whatsoever. There's many different ways that the tire could be slipping. For example, if you slam on the brakes, then the wheels will stop moving, but your car might skid on the road forward, right? And so in that case, the angular, I'm going to use speed now, the angular speed of the tire is 0, but the speed of the car is bigger than 0, right? You could also have a situation where you start from rest and you press on the gas like a lot at the start of the motion of the car. And so the tires are skidding as they spin and try to get traction on the road. And so in that case, the angular speed of the tires is not 0, it's bigger than 0, but the velocity of the car or the speed of the car is 0 because the tires haven't gotten traction on the road yet. So there's no clear relationship between the displacement or the velocity or the acceleration, translation and angular when there's slipping. When there's no slipping, we always have this right here. Okay, we always have this right here. So when there's no slipping, that's supposed to say slipping, not stipping, whatever that is. And then I didn't even put a G. Okay, there we go. Slipping. Placed a little too much there. There we go. Okay, now it's correct. All right, so those relationships are nice because you can now calculate, for example, if you know the angular velocity of the wheel of a car and you know that it's not slipping, which is typically what's happening, right? If the tires on your car are slipping, then you have a problem, right? It means that you're skidding on the road from braking too hard, or it means that you're pushing on the gas too much, and so the car doesn't have traction, the wheels don't have traction, so you're not moving forward. So when you have slipping, that's equivalent to having less control over your vehicle. Okay, so that's maybe a little bit of a note. Slipping slipping. Let me just type it out here. See if I can type it instead, so it looks nicer here. So slipping means no control over the motion of the vehicle. Okay, so that means slipping is a bad thing. When you have no slipping, that's great because then you have control. You can, if you push on the brakes a little bit, then you lower the rotational velocity of the wheel, and so you lower the velocity of the car. Or you push on the gas a little bit, you increase the rotational velocity of the wheel, and therefore you increase the velocity of the car. Okay, let's go ahead and take a look at another example now. I think I need to make a little bit more space here. Okay, so we'll go example 2. Just go ahead and type up the first bit here. So we have a bicycle slows down uniformly. That means constant acceleration, right? From VI equals 8.4 meters per second to rest over a distance of 115 meters. Okay. Tires have a diameter of 68 centimeters. And that's the information we need for the problem. Now we'll go ahead and write part A here. What is the angular velocity of the wheels at t equals 0? So what is omega at t equals 0? Well, we can just say initial. That's fine. So what is the initial angular velocity? Part B, the total number of revolutions each wheel rotates before coming to rest. So revolutions that is revolutions, the total number of revolutions until the tires stop moving. So that's across the full motion of the bicycle. And then this one does have a part C and a part D. So calculate the angular acceleration, assume constant, right? It says uniformly slows down. So what is alpha? And then D, the total time it took until the bicycle came to a rest. So until it's, I'll call that T stop. Okay. So this is a question that mixes some rotational motion with some translational motion. So there are a lot of different ways to go about getting the answers for these parts. I can already just see from experience here, you can probably get a lot of these in different orders and using different methods. So whatever kind of pops out to you first, just go with that method and just work it through. And then maybe I'll put you guys in the break rooms this one, since this is the second example, and then maybe you can talk with your partners. So whoever you end up with, you can talk about how they approached it, or maybe if you guys want to discuss how to do it first and then you both do it the same way, that's fine too. So let me go ahead and set that up now. So I'll do it so that you guys have just one partner each. So the rooms are open. Feel free to join the room now and get started working on this. And maybe we'll limit ourselves to something like 10 minutes for this example. Kevin and Matthew, you guys there? Join your breakout rooms, please. Yeah, that's fine. Yeah. Yeah, maybe I should remind everyone in case they forget that happens. Kevin, are you here? Hello. Do we know what's going on in the problem? Hello? Do you need me to share it with you so you can copy it down? I forgot that it doesn't share. Or do you already have it copied down? Leanne, do you have it copied down yet, or where's the confusion, if there's confusion? Well, just start with the first part. Use what we just discussed. So there's a reason I just went over that. So this is an example of a problem with rolling without slipping. And so that means that this quantity right here is related to the velocity by this expression. Because this is rolling without slipping. So we have a bicycle. We grab the brakes on the bike. So the tires start to slow down. If the tires start to slow down with their angular velocity, then that means that the bicycle's translational velocity as a whole will decrease as well. So that's the starting point. So now we're good, or? Any other questions? Okay. Yeah, if you, I'll be back around. So if you want to see me kind of how I do it, I can show you, and then and maybe that'll help. I'll be back. Let me just check in on all the other groups. Excuse me, all the other groups. Hello? Do we know what's going on in this problem?
A little bit. I'm kind of having trouble starting it.
Okay, so this is an example of rolling without slipping. So what were the equations we just went over?
Oh, the delta x equals delta theta over and the radius
Times the radius, right?
times the radius, yeah.
And then there's another one, the one after that.
Velocity equals omega times the radius.
Right. So since this is a problem where we have a bicycle, right? The motion of the bicycle is given by the motion of its tires, right? So we want to assume there's no slipping here in this problem because it just makes sense, right? If we're riding our bike, there's no slipping unless we like slam on the brakes, right? But we're just coming to rest over some period of time here, 115 meters. No reason to assume there's any kind of slipping. So the idea is to use that equation for rolling without slipping, that V equals omega R.
Okay.
And then that gets you started on part A there, right? So you should be able to get part A. from that. And then from there, it's kind of like it's free game. Like you can just choose many different methods to get the next few quantities there. There's a lot of different ways to do it. So just try to pick something that looks like it'll work and just work it through.
Okay, that helps a lot. Now I know what to do.
Cool. Ju, do you have a question? Do you know what's going on here? You can tell me in chat if you don't have a microphone. Were you able to copy down the question, or I know that was an issue for another group. Okay, so what I was just talking about with Denelise was that in order to do part A, you have to recognize that the tires are rolling without slipping. So if you look at the equations we wrote down for rolling without slipping, one of them was this one. And so the initial angular velocity of the wheel is related to the initial velocity of the bicycle. So the velocity of the bicycle divided by the radius of the wheel would give you the initial angular velocity of the wheel. Does that help? So just basically moving the R to the other side there. If you need a little bit more of like a visual, I'm pulling these examples from the textbook. So if you have the textbook, it's example 8-7. But I don't usually say that because, you know, if you just look at the example in the book, then it's all solved out for you. So you don't actually like solve it yourself. So just be careful about that, but it is there if you want to take a look at it. Okay. I'm going to go check in on the other groups, but I'll come back shortly. How are we doing over here? Do we know what's going on? So this problem is all about what we just talked about, rolling without slipping. Yep, that's exactly what you're supposed to do. Any kind of motion involving wheels, like something on wheels, it's pretty much always going to be a rolling without slipping problem, unless otherwise stated, right? Yeah, and yeah, so that's the idea is you can actually use many different methods to figure that out, right? Because if you just figured out the angular velocity of the wheel, then you could use that to figure out theta and then convert theta to revolutions, right? So there's many different approaches to this problem. Okay, so it seems like you guys are a little bit further along than some other groups. So I'm going to go ahead and let you guys keep thinking and working, and I'll be back shortly. Hello. How are we coming over here? Is it good?
I think we were a little bit confused, but I had totally forgotten that you literally just gave us some relationships when you talked about rolling without slipping.
Yeah. Mm-hmm.
So we pulled out the book just to kind of compare what we're looking at. And right now, at least for myself, I'm on part B.
Uh-huh. Good. So that's exactly it. It's all rolling without slipping and applying those equations. But you can also use those other equations that we had for rotational motion. So once you have omega, you could start thinking about using omega to calculate theta. And then theta's in radians, you can convert that to revolutions, right? So there's a couple different ways to go about this. Just pick a way that, you know, is working. like, pick away and then start working on it. If it's working, it's probably correct. And then, you know what I mean? So there's many
Yeah.
different ways.
If we have, because it gives us the velocity, which is like the translational motion, can we, actually, that's a stupid question. I answered my own question.
Okay.
Um, when I calculated out the first part though, I noticed that the meters over meters, because I got the units basically cancel, so I'm left with seconds to the -1. And I noticed that the book said that they got the same number, but it says that it's radians over seconds. How does that work if you have
Yeah,
no?
so the ratio of the circumference of a circle to its radius is a measure in radians. So
Oh,
in reality, I mean, if you really want to be mathematically precise, um, radians are a unitless quantity, but you can always put radians there as like a placeholder. So yeah, it is meters over meters, right? Which is
yeah.
unitless, but it's
Mhm,
it's it's unitless in a very particular way,
mhm.
involving the ratio of a circumference of a circle to its diameter or to its radius. So we
I
call that
see.
radians.
Okay.
So any quantity like theta, omega, or alpha
Mhm.
always has radians in the numerator.
Oh, always.
Yeah.
Even if it has like, oh, interesting. Okay. It's been a long time since I took any sort of like trig or so. Thank
Yeah.
you.
Uh-huh.
Okay.
All right, I'm going to check in on the next group.
Thank you.
Hello? How are we doing over here?
Doing okay.
Yeah.
I'm doing fine.
We figured out part A.
Part A, what I did was since velocity is equal to angular velocity times radians, not radians, radius, um, I did 8.4 divided by 0.68 meter, which gave me 12.4. But personally, not sure which unit I need to use.
Well, when you write down anything that's angular, it's always going to have radians in there. But technically, you're right that whenever you do like meters over meters, it's kind of unclear, right?
Mhm.
Meters cancel, and you're not really sure if radians should be in there. But whenever you take the ratio of the circumference of something to its radius or diameter, right, we'd call that an angular measurement. So it should have radians.
Got it.
That's what you end up doing. But really, the easiest way to remember is just look at what you're calculating. Is it theta? It has radians. Is it omega? It has radians. If it's alpha, it has radians. So all those quantities should have radians, and then divided by nothing, or divided by seconds, or divided by seconds squared.
Got it. Thank you.
And then Liliana, do you have any question or?
I think I'm good for now.
Okay, yeah. So there's a couple different ways to proceed. Once you have omega, you can do a couple different methods for B, C, and D. So just pick a method and then just work it to the end, and just to see there's many different ways. You guys could do two different methods if you wanted, and then compare. All right, I'm going to go check in on another group. Okay, I'm back. So how's the progress here? Uh, 24.7 for what? For part A. Okay, yeah, that's correct. Well, once you have omega, you can begin to think about how many revolutions, which is related to theta. So revolutions is always related to theta. One revolution is equal to like 2 pi radians. So let me go ahead and share. So you're after this part now, right? So there's a couple different ways to do it. Let me just give you one way, since it'll help get you started. You can use this equation here. So theta final equals theta initial plus omega initial times t plus 1/2 alpha times t squared. But you notice, although you can use this equation, you don't quite have t yet. So you have to think about, how do I figure out what t is? Well, you can figure t out based on the linear motion. By the way, getting t would be like answering question D here. So you can think about, how do I figure out how long it takes for this thing to stop? Well, I could do that with just the translational motion. I don't even have to know anything about the angular motion. I remember all the way back from chapter 2 that distance traveled is equal to 1/2, right? A t squared plus v initial t. And I remember that v final, which in this case would be 0, is equal to v initial times t. Oh, excuse me, not true. Plus a times t. Okay, so all these equations are kind of valid ways of going after different things. And then once you have t, you can get revolutions, right? How would I calculate alpha? Well, one way to calculate alpha here would be to look at just by the definition, for example, omega final minus omega initial divided by, again, delta t here. Okay, but this is another equation where I don't have t. So I could go and get t if I want first. Or maybe I could try another expression. Yeah, and you would also need alpha in that case as well. Maybe let's try an expression that doesn't have t's in it. Let's see, if I have velocities, final velocity squared is equal to initial velocity squared plus twice a times the displacement. So here's an equation without t. How would I translate this equation to an angular equation, or a rotational equation rather? So we did look at that earlier. So maybe if I can use this equation, I don't have to get the time first, right? And it just becomes a matter of figuring out, and none of these particular ways of going about this problem are the wrong way, okay? There's definitely, if I just go through some method, I will get the answers to all 4 of these parts eventually, okay? So pick something that seems like it will work. And of course, eventually it will work if you massage the equations enough. So do you guys want to ask any more questions about that, or is that kind of enough to get you started thinking about it without giving away too much? Is that good, or should I talk a little bit more? I can talk a little bit more. I don't mind. I just want to get you to the point where you kind of feel like you know what to do, and then you can just start doing it and see that it works. No 9.8 in this course. There's no free fall. Nothing is falling under the influence of gravity. Nothing is falling under the influence of gravity here. So one way to do this problem, let me go ahead and I'm actually just going to delete all this. I have some space here. Hopefully you had time to write it down. If you didn't have time to write it down, we did already write this down from earlier in the lecture, right? All those equations. One way to do this question here would be to think about the connection between the 115 meters and how that's connected to the revolutions that the tire has to go through. Okay, so technically speaking, this would be the quickest way to the answer. So let me not say too much. Let me just say that. Do you guys, does that help? Does that get you like, is that a big enough hint, so to speak? So there may be some connection that we discussed between the displacement, the translational displacement, and the number of revolutions that this tire will go through. Does that make sense? No, what did you do for part A? What did you do for part A? You use this equation, right? Because it's without slipping. So what's the equation without slipping for delta x? What's the equation for slipping without slipping for delta x? Right, delta theta times r. Can I get revolutions from this, from delta theta? What units are theta going to be in? Not degrees, but radians. Always radians, okay? Make sure that your calculator is always set to radian mode. It's actually super important in this chapter that you're always in radians, never degrees. So make sure it's radians. And then once you know theta in radians, how do I go from radians to revolutions? How do I go from radians to revolutions? Two pi equals 1 revolution, right? 2 pi radians equals 1 revolution. Does that make sense, Leanne? Are you with us? Okay. So that's going to get you all the way to the answer on part B, right? So once you recognize that it's rolling without slipping, then you have this expression right here. Delta x is delta theta times r. So solve for theta, so delta x divided by r is delta theta. And then you take delta theta, which is in radians, and you got to divide it by 2 pi, right? So if I have radians here, then 2 pi radians is 1 revolution, right? like if I have theta radians, then this will give me theta revolutions. Maybe we should use another symbol here. If I have some number of radians here, then I will divide it by 2 pi and I will get some number of revolutions on the other side. Okay. Once you have that, again, you can kind of use the same method of rolling without slipping to find alpha, or you can use another method, and really all the methods work. You don't have to always use the rolling without slipping equations, but they probably, for this particular problem, they are maybe going to be the easiest. All right, so I'm going to go ahead and check in on the other groups now, and I'll be back again. Hopefully you guys are able to figure that out for C and D, but I'll be back. Hello. How are we doing over here?
We're doing good. We moved on to part B. For part A, we got 24.7 meters per second.
I think that sounds right. Yeah.
Okay. And then for part B, we got 53.8 revolutions.
53.8.
Yeah.
That's the correct answer. Yeah.
Okay.
How did you get that?
I used the equation V equals omega times the radius. Yeah, and then just isolated omega. Wait, no. What did I do? I wrote it here.
Yeah, there's many different ways to go about it. I think the rolling without slipping equations are probably the quickest way to get to the answer. But you could obviously use a lot of those other equations we talked about earlier as well. It's just you have to maybe do the questions in a different order.
Yeah, so actually for part B, I did the delta x equals delta theta times radius, and I isolated delta theta and converted to the revolutions.
Right.
Yeah, we're doing part C now. I'm looking at the equations from earlier to see what I can work with.
Okay, Jude, do you have anything you want to add to that? Do you have any questions or anything you want to add to that? Okay, so I'll check in on you guys in a bit then.
Okay. Sounds good.
Hello? Do we have any questions here? Are we figuring things out? How are we doing? Have we figured stuff out here? What part are we on? A bit confused on how to find the total revolutions. Okay. Got most of the other parts. So there's a couple different methods to go about doing it, but probably the easiest method is to use the equations that we talked about for rolling without slipping. So there's an equation that relates the total displacement to the angular displacement. And then once you get the angular displacement, you can convert that to revolutions. So what is the equation that I'm talking about? Yes, delta theta equals delta x divided by r, exactly. And then once you have delta theta, you can convert that. Yeah, everything for these angular quantities will always have units of radians in this class. We never want to have anything except radians. Otherwise, it messes with our equations a little bit. So you can always get an answer and then convert it to revolutions or revolutions per minute or something like that. 53.8 revolutions sounds right. Let me check it. Yeah, that's the correct answer. Yeah. So Matthew, are you? Does that make sense? What we were talking about there? So you want to use the rolling without slipping equations. So delta x is equal to delta theta times r. Does that make sense? And then once you solve for delta theta, then that answer that you get is in radians, not revolutions. So in order to convert between radians and revolutions, you've got to divide by 2 pi, right? Because 2 pi is 1 full revolution, like a whole circle, right? And then you got, so you have omega I, T, and alpha. 27.4 for the time, and alpha negative 0.9 roughly. Yeah, that's good. How about you, Matthew? Are you catching up to her on that now, or did you also have the time and alpha already? Oh, okay, good. Yeah, that's good. So you guys are pretty much done. So you could just go back to the main room when you're finished and you're comfortable with that. I'm gonna go check on another group now. Okay, how are we doing here? Have we figured it out?
Yeah, I think so.
Okay. So if you guys are done, then you can go. You can just join the main thing. I think I'm gonna close the rooms here in a second.
Okay, thank you.
I just announced that I'm gonna close the room soon, and then I'll just go over the problem. So we're just hang tight here for a minute. Couple more seconds here before the rooms are fully closed. Okay, welcome back everyone. I'm gonna go ahead and go over the question now. So those of you who maybe need a little bit more time, you'll see how to do things here. But then later you can go over the question again by yourself to make sure you can get it, right? So how do we get omega, the initial angular velocity of the wheel? Well, we do that by using the equation omega I times r is equal to vi. So the translational motion is equal to the radius times the angular motion of the tire. Okay, and we can solve this equation for omega I, and it's simply the angular velocity of the tire is equal to the translational velocity divided by the radius of the tire there. So if you plug in the numbers on that, 8.4 meters per second divided by 68 centimeters, but convert that into meters. So 0.68 meters. And then you have to realize that we're looking at an angular velocity here. And so when I take the ratio meters to meters, what I'm really doing is looking at the ratio of something like the circumference of a circle to its radius or to its diameter. And so that gives us units of radians. And so the units here will be radians per second. Oh, and actually, yeah, I just realized, thank you for pointing that out to me. This is not the radius here. This is actually the diameter here. So let's go ahead and fix that up real quick. Oh, whoops. There we go. So we'll fix that up real quick. So that's 34.34 meters because it's the diameter here. So diameter over 2 equals the radius. And so for the actual numerical answer here, what do we get? We get 24.7 radians per second. Okay. All right, let's switch maybe orange here for the part B. To get the revolutions, probably the simplest way is to use the equation delta x is equal to delta theta times r. Okay, but there are many different ways. So remember I said there were many different ways. I think only one group actually went about the order of the problems differently. So you can check with them that indeed you can do these in another order by using different equations. So delta x equals delta theta times r. This is the equation that says the total distance that you travel in the x direction is related to the distance that you go around the tire, right? Because the tire is making contact with that road, right? And there's no slipping. So the amount that you go around the tire is going to be related to the amount that you travel forward. Once we solve this equation for delta theta, we're going to have an answer in radians, not revolutions. So delta x divided by r here is 115 meters divided by the radius, 0.34 meters, right? And then once we get this answer, again, we have meters divided by meters, but it's an amount of translation in the x direction, which is related to the amount that we go around a circle, right? And so when we take that amount that we go around a circle, that's kind of like a circumference, not exactly, and then divide that by the radius of the circle. So that's going to be a measure in radians, okay? And the value that we get here for this, let me calculate it real quick, unless somebody already has it. 115 divided by 0.34 is 338 roughly. Put a little approximately here, 338 radians. Okay, and that's in radians. Let's convert that to revolutions now. So we have to use the fact that 1 revolution is 2 pi radians. So we can take this number and divide it by 2 pi. So 338, I'll just write it like this. So 338 divided by 2 pi. And what we end up with here is 53.8 revolutions. So there is the answer. Let's go ahead and box our answers here. Box this one, box this one. We'll just go through the colors of the rainbow here as we go through the parts. So yellow is up next, but let me know if maybe I'll use this darker yellow so it's a little bit easier to see. So for the next part, we're looking at calculating alpha. Now, we're not given an acceleration in this problem, a translational acceleration, but we're told it's a uniform acceleration. So it slows down uniformly. So we can use that information that is constant to apply our simple definition that delta omega actually maybe we want to use the equation that doesn't involve time. If we want to do the last part, which is to calculate the time, if we really want to go in order here, we'll calculate alpha without any information about the time. So here's what we'll do. We'll use the equation omega final squared, that's an F there. Let's try to write that better. Omega final squared is equal to omega initial squared plus 2 times alpha times delta theta. Okay, now this equation doesn't have a time in it, right? So we can do this before we calculate part D. The initial omega is not 0, but the final omega is 0. So let's go ahead and X this one out. That's 0. And we're solving this thing for alpha. So if we want to solve for alpha here, alpha is going to be equal to minus omega initial squared. I'll let you guys figure the algebra out on this. It's not too bad, okay? Give it a shot. Divided by 2 delta theta. Minus omega initial squared divided by twice delta theta. We can go ahead and plug in everything we've already calculated. We've already calculated omega initial and delta theta. So that's going to look like minus 20, and let's go, maybe we can color code these. So 24.7 squared. And then we're going to have on the bottom 2 times delta theta. Delta theta is in orange here. Make sure you use delta theta in radians. Do not plug in revolutions here by mistake. It has to be 338 radians. Actually, I'll just go ahead and leave the units off here, since I already chose to leave them off for the other quantities there. So what we get in the end here, and I'll just cheat, I see the answer right over here. It's minus 0.902, and the units are radians per second squared. Go ahead and box that one. For the time that it takes to stop, what's the next color in the rainbow? Green, right? For the amount of time that it takes to stop, well, we can use the fact that the final angular velocity is equal to the initial angular velocity plus the angular acceleration times the time. Okay, so here's one of our rotational kinematic equations. We'll solve this for t. And don't forget that alpha here is a negative number. Okay, we want to make sure we plug in a negative value for alpha. Okay, so when we solve this here, again, I'll let you guys handle the algebra there. T is going to be equal to omega final minus omega initial divided by alpha. And you can see here that omega final is 0. So we have minus omega initial on top. So minus omega initial is 24.7 radians. And alpha is minus oops, wrong yellow, minus 0.902 radians per second squared. And we can see that the minus signs there cancel. That's going to be 2 pluses. And we get for this answer here, I just look at the answer again, 27.4 seconds. Okay. So are there any questions about that? Is it now a little bit more clear? A couple groups were struggling a little bit. So does that help make things more clear? You can just give me a thumbs up if you're good to move forward on that. If you have a question, just let me know. Can everybody give me a thumbs up again? I'm not sure if there was any, if there's. Okay, I think that's everybody. Let me know if there's a question, okay? Just stop me and ask your question. But now we're done kind of with this idea of rolling without slipping. And the next section that we need to talk about is what we call torque. Now, I'd kind of like to draw an analogy between torque and force. Torque is basically like a rotational force, is really what it is. And there's a lot of similarities in how we set those things up. So let me just remind you guys that force, we can write the net force on an object is equal to its mass times its acceleration. Okay. Now, when we apply a force to an object, the center of mass of that object will begin to move. And what we saw in the last chapter was that, so maybe let me back up for a second here. So in the last chapter, we talked about center mass. We didn't have great coverage of it in the lecture. But let me just remind you what center of mass is. So if I'm interested in the X center of mass and the Y center of mass of an object, the meaning of these two quantities, X center mass and Y center mass, is that I can treat a large, complicated object, for example, a planet, as if it were a point with all of its mass concentrated at the location of the center of mass. So that's the whole point behind the center of mass, is that what you're doing is you're calculating this weighted average of where all of the different masses are in this large body. And you're figuring out where is the point in this object where I can treat this very large and complicated object as if it were just a point with all of the mass concentrated at that point. So that's the idea behind the center of mass. And then on the bottom here, I'll just write M total. And of course, the location of the center of mass, again, you can break it down into components. And so you can calculate the X coordinate of the center of mass and the Y coordinate of the center of mass by simply breaking down the position vectors into their components. So let me just go ahead and finish writing this equation here, and then finally divide this by the total mass of the object. And so what you guys saw in the last chapter was that if I have, let's say, a sphere here, well, the center of mass of a sphere, if this sphere has a uniform mass distribution, is just simply the center of the sphere. Okay, so the center of mass of a sphere is just its center. Now, for a rod, again, with a uniform mass distribution here. Again, the center of mass is right in the center. Okay. Now things get a little bit complicated. For example, if you have like a triangle, like an equilateral triangle, then the x center of mass will be, you know, half the distance, and then the y center of mass will actually be 1/3 of the distance there, 1/3 of the height. That's for a equilateral triangle with side lengths 1. And when you have continuous bodies like a triangle, you know, let's say you have these like a metal sheet and you cut it into a triangle, right? The masses are everywhere. So you need to have calculus in order to calculate where the center of mass is if you want to do it rigorously with the formulas that we just wrote down up here. For a sphere, I think it's pretty intuitive that a sphere, the center of mass is going to be in the middle, provided that sphere has a uniform distribution of mass. Again, you could prove that using calculus. Even those of you who are in the 210 class, I will not ask you to prove something like that. But what do you do once you have the center of mass? Well, once you have the center of mass, that literally is the point that you can treat the object as if it were a point mass. So center of mass, let me actually write this out for you guys so you maybe you can copy it into your notes here. Whoops. Okay. Mouse is giving me trouble here. There we go. So center of mass is a special point where a complex object can be treated as if it were a point mass with all of the mass concentrated at the center of mass. So that is literally the meaning of the center of mass. Center of mass is a special point where a complex object can be treated as if it were a point mass with all the mass concentrated at that center of mass. Okay. And why is that the case? Well, you can actually take these two equations up here and calculate delta x, center of mass, and divide it by delta t. And what you see is that on the right-hand side, you get the sum of all of the momentum of the individual masses in the system. And on the left-hand side, you can get the total momentum of the system calculated via the center of mass. But in order to see that, you have to put the total mass on the left side. So I'm going to go ahead and show that now. So again, here's what, let me just outline again, because I think you guys are probably still copying this. You guys are probably still copying this down. So let me just go ahead and say what I just said again. I'm going to take delta of this equation up here, delta x center of mass, and I'm going to divide it by delta t, and I'm going to multiply by the total mass from the right hand side. I'm going to move it over to the other side. Okay, so that's what I'm going to do here. So the sum of all of the masses in a system, we'll look at just 1D. The sum of all of the mass in a system times the x center of mass, this is just m total here, is equal to, again, and by the way, I'm just copying the equation down that I had before, is equal to m sub I, x sub I, sum over I. Okay. So the total mass times the center of mass position of some complex object with some crazy distribution of mass. It could be a galaxy and there's just trillions of stars and planets all over the place. There's no clear way to describe that system. Well, we could calculate its center of mass, and then we could describe that system very easily as if the entire galaxy was just a point. Okay, is equal to the sum. Again, I'm just writing the exact same equation again. Now I've substituted in mass total for m sub I. Now I'm going to do the new thing here. What I'm going to do is I'm going to calculate the delta of this equation here. So I'm going to take the delta of this thing. I'm going to divide both sides by delta t, okay? Divide both sides by delta t. So what does that look like? Well, the total mass of the system is not going to change. Let's suppose we're talking about a galaxy, right? The mass of the galaxy is just the mass of the galaxy. Sum up all the masses of each of the individual stars, planets, whatever's in the galaxy. Okay? But the position of the center mass might change if the galaxy is moving, right? You look at these big clusters of galaxies, using like Hubble Space Telescope or something, right? You observe these galaxies and you see clusters of galaxies, and obviously there's gravitational forces between those galaxies. So those galaxies are moving through space. So the center of mass can change. The location of the center of mass can change if the object is moving. Okay? We're dividing this equation by delta t. Well, you can clearly see that this expression delta x over delta t looks like a velocity, and it is. Let's see what happens on the left side now. On the left side, again, none of the masses are changing. None of the masses are changing here. But the positions of the masses could be changing. I forgot my delta here. The position of the masses could be changing, right? You look in a galaxy and what's the galaxy doing? All the stars and everything are spiraling around the center of the galaxy, right? All the planets are spiraling around their stars. All of the moons are spiraling around their planets. And of course, all the stars and everything is spiraling around the galaxy, right? So the positions of the masses change. All these different positions of all these different stars and planets are changing. But what this equation tells us is that we can describe the entire system of all these trillions of stars and planets in terms of simply the total center of mass of that system. So you take all the mass and concentrate it at a single point. That's the beauty of this equation here. Okay? And now what's going on over here on the right-hand side? On the left-hand side, we replace delta x center of mass over delta t with v center of mass. And so we have the total mass times v center of mass, the velocity of the center of mass. On the right-hand side, we have the sum of the masses times their respective velocities. You might recognize this as the sum of all of the momenta of those masses. So the sum of all of the individual momenta of those masses in that galaxy, all the stars, all the planets and their moons, and all the asteroids and comets, all combine. And what it tells you is that instead of looking at this as a complex system with trillions and trillions of different objects, I can look at this as simply the total mass of that system times the velocity of its center of mass. And of course, on the right-hand side of this expression, this is nothing but the total momentum of that system. So the total momentum of the system, instead of summing up trillions of different velocity vectors times their respective masses, I can calculate the total momentum of the object as simply the total mass of the object. And astronomers have really good methods of calculating the total mass of a galaxy based on how it's moving relative to other galaxies. So when you look at clusters of galaxies, they're kind of orbiting each other, not too much differently than what we did in our section on circular motion, right? Circular orbits. Of course, these orbits are a little bit more complicated, but astronomers have really good ways of measuring the total mass of a galaxy without looking at each individual mass and summing them all up. And so it's much easier to get the total mass of a system and then multiply by its velocity of the center of mass than it is to sum up all of the individual momenta of the system. So that's the beauty of this expression right here, is that the total mass of the system times the velocity of its center of mass of a very complicated system. We can just treat this thing as if it were a point with all the mass concentrated at a point. That gives us the total momentum of that complex system there. That is a very important equation there. Now that was from the last chapter, okay? But from this equation, of course, we know about impulse. We know the relationship between force and a change in momentum, okay? And so if we were to put the total momentum of the center of mass of an object on the right-hand side, then on the left-hand side, we would have the net external force. And whenever we have no net external force, the total momentum of the system is conserved. I think you guys remember that. So if the net external force, sorry for the handwriting here, the mouse is kind of giving me some trouble. The net external force is 0. And you guys notice I've left off a lot of vector signs here. Feel free to add in the vector signs if you want to, but for what we're about to do, the vector signs are not necessarily that important just yet. So if the net external force is 0, then that implies that the total momentum, I should say the change in total momentum is 0, right? That means that momentum is conserved. Okay, so hopefully you guys remember that. These concepts will be on the test, right? So you do want to go back and review these concepts. So when the net external force is 0, the change in total momentum is 0. And that really is the net external force. Remember, if I take a galaxy and I look at the forces between, for example, some planets and their stars, of course, those forces are internal forces, right? Those are forces that are inside of the galaxy. But remember, we also have Newton's third law. Newton's third law says the force of gravity between a star and a planet on the star is equal and opposite to the force on the planet. So those equal and opposite forces cancel out when we sum up all of the forces on those objects. So Newton's third law is actually very crucial there for momentum conservation. Okay, momentum conservation is a consequence of Newton's third law. Okay, so where are we going? How does this relate to what we're doing in this chapter, which is rotational motion? Well, there are situations in which the net force on an object can be 0. I will show you a situation now. Here's a force on an object. I'll label the center of mass here for this, this rod here. So we have a rigid rod here. We have a rigid rod. What is a rigid rod? It just means it's a rod that doesn't change its shape. So rigid rod with no net force. Okay, so we have a rigid rod with no net force here. Why is it no net force? Well, it's not no net force just yet, but we're going to make it no net force. If I apply a force in this direction, which has this magnitude, I could also apply a force in this direction over here of equal and opposite direction. So equal magnitude, but opposite direction. I think you guys have very good intuition as to what's going to happen if you take, some rod like this. Take your ruler right now and set it on your desk, and just use your fingers to push. Push with one finger in this direction on the left, push with the other finger in this direction on the right. What happens to that ruler? Well, the ruler starts rotating, right? The rod is rotating. The rod begins to rotate. However, there is one crucial bit of information that we know from what we studied in the previous chapter, which is what I just covered. And that is that the center of mass does not move. Why does the center of mass not move? Why does the center of mass not move? Does anybody want to answer this one, or you guys just want me to give the answer? Why does the center of mass not move? You should be able to see from this equation that is still on the screen here. Right? The center of mass is not going to move because there's no net force. We have an equal and opposite external force, two equal and opposite external forces acting on this rigid rod. And when we sum up the net force, we get 0. So that implies that the center of mass does not move. It is in equilibrium. Well, we know that this object is going to rotate. Well, that seems to be something that we need to sort out, because if I'm going to say that this object, the center of mass of this object doesn't move, well, that's not good enough, right? We know that this object is going to rotate because we can just push on a ruler, for example, and it will start to rotate. So how do we describe the object now that we have a situation where we have no net force, but we definitely know the object is going to do something? And so we would have said previously that this object would be in equilibrium if it had no net force on it. But now we know that this object is going to rotate. And so maybe we should redefine what we mean by equilibrium. Okay? And that's exactly what we're going to do. Okay, so how do we describe the rotation? That's what we're going to work on now. And we've already done the groundwork for that using our rotational kinematic equations. Oh, I went down a little too far there. Here we go. And the idea is that now we introduce a quantity called torque. Torque has the Greek letter tau as its symbol, T-A-U. And what a torque is a force times a lever arm. I'm going to write it as like force times lever arm, F times L. However, it is very important that the force is perpendicular to the lever arm. Otherwise, there would be no rotation for that object. If I applied a force directly through the center of mass of this object, then the lever arm would be 0, and this object would simply translate. It would not rotate. So for the green force here, there would only be translation, there would be no rotation. Now, a lever arm is a distance that we measure from the center of mass to the location of the force. Now I say it's that the lever arm is a distance measured from the center of mass to where the force is applied, but it doesn't necessarily have to be the distance from the center of mass to where the force is applied. It could be the distance from any point to where the force is applied, but it's so much easier to calculate the torque if you measure the distance from the center of mass. So that's how I'll focus on showing you guys what to do here. So we're going to focus as if L is measured from the center of mass here. So we can even maybe subscript that for now. We can say L is measured from the center of mass here, and we need the force to be perpendicular. And then the next logical thing to do here, maybe it's not so obvious, but the next logical thing to do here would be to say that if we have a torque, then we want to make a statement something like torque is proportional to angular acceleration. And sorry that there's a repetition of symbols here. This is alpha meaning proportional to. This doesn't happen very often in physics, but sometimes it happens where we have kind of the same symbols. So proportional to, and this one right here is angular acceleration. So just like force is proportional to translational, oh my goodness, there we go. I'll stop writing there since it's giving me trouble. Just like force is proportional to acceleration, tau, the torque, is going to be proportional to angular acceleration. We can actually show that. We can actually show for a simple case. Give like a simple derivation to show that right now. So what we'll do is we'll imagine, first we'll write down the equation F equals ma here. And we'll imagine a case for a wheel here. So we imagine a case for a wheel which has a radius r. Let's do a little bit bigger here. Maybe we can do this shape here like this, and we can get a line like this from the center here, like that, right? And this is the radius r. Okay, and then this thing is going to roll on a surface. And I meant for the surface to be level here, so let's try and fix that, like so. If F equals ma, then what I can do is I can multiply both sides of this equation by r. Actually, I want to multiply. Here's what I want to do. So acceleration in the translational acceleration is given as alpha times r, right? And so what I want to do is replace a with alpha times r. That's what I want to do here. So replace a with alpha times r. So m times alpha times r here. Okay. And then write this equation again here as F equals m alpha r. And then I want to take a look here. And actually I used red for the radius, so I wanted to use red for the force, but bear with me here on this one. So the force of friction between the tire and the road is really the force that moves the wheel, right? So the force between the road and on the tire is the force that generates the motion of your car or your bicycle. And so that force is acting at a distance r from the lever arm. So our lever arm distance here is r, okay? And so if I take this expression, let me give myself some more space here, if I can. Oh, it doesn't let me actually go. Okay, we're gonna maybe need to scroll this over here for a second. How do I want to do? Maybe, okay, maybe I can just bring this over here like this, and then maybe clean up some of this here. So keep this here. Oops, there we go. There we go. Okay. So we'll keep this here like this. I don't want to open up a new thing and lose my diagram here. So we'll go like this, and then let me rewrite that equation again. Bear with me here for a second. So what did we have here? Force times F equals m alpha r. Okay. But since we have, this must be equal to the force here that's on this tire. Okay. Since this is the force on the tire, notice that it's perpendicular to the lever arm R, which is the lever arm measured from the center of mass of the tire out to the edge of the tire here. Okay. And if this is the force on the tire, then we can write down an expression for the torque. And the expression for the torque, remember, is R, well, in this, let's be careful here. It's the force on the tire that's perpendicular, which happens to be F, times the lever arm, right? So force times lever arm, and again, measured from the center of mass here, we can write this again. Right? But of course, the force here is already perpendicular, so we'll just replace that with F. And then the lever arm is just R, right? So we'll replace that with R, right? And so now if we take the force that we have and substitute it into the expression here, we have that the force is m alpha r. So, and maybe we can color code this a little bit. We're going to take this, plug it in over here. So m alpha r times r. And what we end up with is mr squared, and I want to put this term now in parentheses, times alpha. And now we can see the relationship between the torque and the angular acceleration. Remember we said that torque was proportional to angular acceleration? Now we know that the proportionality constant is this thing mr squared, okay? Now mr squared, we have a name for that. We call it moment of inertia. And we use the symbol capital I. We call this moment of inertia. And this is where things start to get a little bit complicated in this chapter here. Moment of inertia is a little bit of a kind of a difficult concept to kind of wrap our minds around. But what moment of inertia essentially is, if you recall, F equals ma, what is mass? Mass is like an object's resistance to change in motion. The more mass an object has, it's harder to change its motion. In this case, the more inertia, moment of inertia an object has, the harder it is to change its angular motion or its rotational motion. So let's go ahead and put that in writing, because that's a little bit, that's a concept we really want to make sure we can wrap our minds around. If we can understand that, it really helps us do these problems. So So for so let's say for translation or translational motion, F equals ma. Mass, well, let's try and put it in like as simple as we can. So more mass means more resistance to change in motion. For rotational motion, how am I going to write a tau here? That's going to be tough. Here's what I'll do. I'll just put it like this. I'm leaving some blanks in. I'm going to write them in here in a second with the actual pen. For rotation, more moment of inertia means more resistance to change in rotational motion. So let me fix that in the top sentence there. And then I'll just use the pen here to write in the symbol tau, the square, and the alpha here. And this quantity here we call I, which is moment of inertia. Okay, so for rotational motion, the more moment of inertia, the bigger the moment of inertia, the more resistance to change in rotational motion. So I think we can see, if I finally write down the equation in this form here, tau equals I times alpha. If I apply a torque, a fixed amount of torque to an object, let's say I apply 100 units of torque. If I is really big, I'm not going to get much angular acceleration. If I is small, I'm going to get a big angular acceleration. So depending on, like if I fix an amount of torque that I apply to an object, depending on I can get a bigger or a smaller angular acceleration. So that's really the idea here, is to draw an analogy between the idea of force that we already developed and torque, which is the new concept that we're developing for rotational motion. So a force and a torque are kind of related. Torque is rotational force in a certain sense. And moment of inertia is almost like an object's rotational mass. So it's kind of like a strange idea, right? That an object would have a rotational mass. And angular acceleration, or rather acceleration, angular acceleration is kind of like an object's acceleration around in a circle, right? So we have these analogies between these quantities here, and we really want to try and draw as many analogies as we can to try and understand what's going on here. But there is some new physics that comes up as a result of this new concept of torque. But before we get further into any new stuff here, remember what we did. We reviewed kind of the idea of center of mass, and then we introduced the concept of torque. And we oftentimes want to make sure that we calculate the torque relative to the center of mass of an object. And that makes our calculations a little bit easier. Let's go ahead and do an example now with torque. And so I'm going to go ahead and I need to actually create some space here. I need to actually start a new file here. Can you guys just give me a thumbs up if you're done copying this down? So give me a thumbs up if you're done copying this down so we can do an example. I have to clear this so we have a blank slate here. Okay, Matthew, Sammy, do you guys need more time? Matthew. Okay, I'm going to go ahead and create a new slide here. Okay, so this is another example, example 3. Okay, so suppose we apply, suppose we have a similar situation here where we have this wheel. We'll get a nice diagram going here. So we have a wheel, if I can write, there we go. So we have a wheel and we have a torque that's going to be applied to this wheel here. And the torque is going to be applied due to some mechanism similar to a bicycle wheel. Okay, so there's some mechanism here with a bike chain that's going to apply a torque on this wheel. And the torque on this wheel is going to be applied in such a way that the rotational motion that is caused by the torque will be in that direction there. Okay. And the magnitude of the torque here, let's say, is going to be 40 Newton meters. If you were wondering about the units of torque, there they are. It's force times lever arm. Force is measured in newtons, lever arm measured in meters, so Newton meter. Now it turns out that the units of torque, newtons times meters, is the same as joules, but we never write the units of torque as joules because joule is reserved for units of energy and torque is not related to energy. Torque is a separate concept from energy, so we use newtons per meter. Now, a bicycle wheel can be treated as a ring with the vast majority of the mass concentrated on the edge of the ring. And that's going to be the next concept that we talk about, is how to calculate moments of inertia for different objects. But for now, let me just come up with a value here for the moment of inertia. We're going to say that the moment of inertia here is 80 kilogram times meters squared. Again, another bizarre set of units for this quantity here, moment of inertia. But remember, moment of inertia is like mass times distance squared, mass times radius squared. So that's kilograms times meters squared. Okay, so we're going to turn this question into a couple different parts here. So the first, and maybe the most obvious, we just introduced the concept of torque. Let's calculate the angular acceleration here for this system, right? What is the angular acceleration? For part B, maybe we can calculate an angular velocity if we assume here that this torque is being applied, let's say for 3 seconds. Something simple, keep it simple, right? Okay, and then maybe again, it's good to get some practice. How many revolutions? If I can write an R here, my mouse is giving me trouble. Okay, we'll stop it right there. We don't want to do too many parts here. Okay, so that's the task here. Now here's how I want to do. Here's how I want to do this. I think these 3 parts are fairly straightforward. Let's go ahead and combine this example problem with some break time, because we've been going for a long time. We really never took a break. Let's go ahead and take a break. So I'll give you guys 10 minutes. I think you can do these 3 parts in about 5 minutes. We already kind of know how to do parts B and C from the previous example. Part A is the only new part here, and it's fairly straightforward. So we'll go ahead and take 10 minutes. Any leftover time you have, take as a break, okay? So we'll meet back here in 10 minutes. So let's go ahead and say 9:08. We'll meet back here, or excuse me, what am I saying, 9:08? 8:17, or 8:18 we'll say. So meet back here at 8:18. I don't know if I can remove the 9:08 message. It doesn't look like it. So we'll meet back at 8:18 p.m. Work on this example. If it takes you a little bit longer than 5 minutes, then it's going to take a little bit of the break time. But I think 5 minutes is plenty to finish this off. So put any answers that you calculate in the chat so others can compare. And then, if you finish part A, put part A. If you finish part B, put part B. And then I'll check back in with you guys in the 10 minutes, okay? So enjoy your short break, and we'll be back to continue with torque and rotational kinetic energy and then angular momentum. Okay, we're back. Let's take a look here. So to get alpha, apply that equation that we just kind of introduced. That torque is moment of inertia times angular acceleration. It's like F equals ma for rotation. So we've got 40 over 80 for alpha, which is half a radian per second squared. So 0.5 is fine. How about for omega after 3 seconds? Well, omega final is equal to omega initial plus alpha t, using the rotational kinematics equations. Omega initial is 0. Well, I guess I never said that. Maybe I should have said that we begin at rest. Sorry about that. That's the only way to do this problem, is to just assume omega I is 0. So 1/2 radian per second squared times t, so it's 1/2 times 3, which is 3 halves. And this would be radians per second. To get revolutions, we first go for delta theta, or well, rather I could put theta final here, is theta initial plus omega initial, which is 0, plus 1/2 alpha t squared. And so the amount of theta that we're going to rotate through, theta initial is also 0, is 1/2 alpha t squared. So 1/2 times 1/2 times 3 squared, that's 9 over 4 radians. We want to convert this to revolutions, so divide it by 2 pi. So revolutions is 9 over 8 pi. For the answer there, we can go ahead and plug that into the calculator real quick. 9 divided by 8 pi is 0.36 roughly, so 0.36. Okay, are these the answers that you guys were getting? I believe so. Yep, it looks like you guys were getting these, except maybe, okay. Then at least check your part C. Okay, not many people gave answers here. Did you forget to divide by 2 pi? Maybe you divided by pi, so it looks like you're off by a factor of 2. Okay, so that's an example there. Any questions about that? Give me a thumbs up if we're ready to move on to the next thing. Okay. Move on to the next thing here. Just like in Newton's laws, we have that the sum of all of the forces is equal to the net force, and it's mass times acceleration only for the net force. We have a similar thing for torque. Okay, torque is a vector, but in order to understand the vector nature of the torque, we have to introduce what's called the right-hand rule. And I don't know if I can, is this my right hand as you guys see it? Is this my right hand to you guys? Can you guys tell that this is my right hand, or is the image flipped? Some of you are giving a thumbs up. Is this my right hand? I need some more In any case, we'll figure it out when we get there. We have the same situation for torque, okay? We have to sum all of the individual torques. How are we going to have more than one torque in a problem? Well, we're going to have more than one torque if we have more than one force that's generating a torque, right? So if you have more than one force that's trying to rotate an object, then we're going to have more than one torque. We say that this is the net torque here. And it's only the net torque that equals I times alpha. Okay, it's only the net torque. In the last problem, I gave you the net torque. I just said, here's the torque, right? And I told you the moment of inertia there. Let's see how the moment of inertia actually is calculated. The way that we calculate the moment of inertia is we suppose we have some torque here. And this torque acts on some part of our object. And that part of our object is at some location, r, from the center of mass. And there's, of course, an angular acceleration associated with that, alpha. And now if our object is a rigid object, of course, alpha is the same for all of the masses in that rigid object. That's maybe something I forgot to mention. Omega is the same for every point omega is the same for every mass in a rigid body. Every little bit of mass inside of an object will have the same angular velocity. But the actual velocities of those objects could be different depending on how far away they are from the center of mass. And of course, the mass that is located at the center of mass has zero velocity, right? By definition. Okay, so what we do is we sum these torques to get the net torque, right? And what happens is we have a summation on the right-hand side, which sums over all of these m sub I, r sub I squareds. And we have to do this summation to figure out what the moment of inertia is of an object. So the moment of inertia of an object is defined as this summation here. And for those of you who are in the calculus class, I won't ask you to do this, but this summation becomes an integral when you have a continuous distribution of masses. So if you have like a sphere with a constant density, or like a cylinder with a constant density, you have to do like an integral to figure out what that formula is going to be. But there it is. That's how you calculate the moment of inertia. And so you can calculate the moment of inertia of a simple system now. Let's go ahead and do that. We'll calculate the moment of inertia of a simple system here. We have two masses, let's say 2 kilograms. Well, let's make it simple. This one will be 1 kilogram. And then this one here, a little bit bigger. This one will be 2 kilograms. And the distance between these two masses, maybe we'll call it L. Okay. So this is an example here. Let me go ahead and walk you guys through, since this is the first time we're seeing like a formula kind of like this. If I want to calculate the moment of inertia here, let's go ahead and just pick, well, first off, I mentioned, okay, sometimes things are a lot easier if we calculate moment of inertia or torques from the center of mass. So let's first calculate the center of mass. So where is X center of mass for this system? That's going to be part A. And in part B, what is the moment of inertia of this system? So those are the two parts there. How do we get x center of mass? Well, the x center of mass is that weighted average divided by the total mass. So it's going to be m1 x1. Sorry about the mouse here. m1 x1 plus m2 x2 over m1 plus m2. But we need, what do we use for x1 and x2? Well, we don't know where the center of mass is yet. So let's pick a coordinate system for ourselves, okay? I'll choose this coordinate system right here. That way x1 is 0. That's a nice little trick that you can do. Pick your coordinate system to be at one of the masses so that its x distance is 0. So if I do that, what I end up with is m1, 1 kilogram, x1 is 0, plus m2 is 2 kilograms, x2 is L, and divided by the total mass, which is 1 plus 2, which is 3. And what we end up with is the x center of mass is 2/3 L. So somewhere over here. And that makes a lot of sense because we have more mass on that side. So this distance right here is 2/3 L. Then this distance right here would obviously be 1/3 L, right? Okay, now let's calculate the moment of inertia. Okay, so for the moment of inertia, it's not m times x, it's m times x squared now. Okay, so this, and there's no division by the total mass either. So summation over I of mi ri squared. We're working only with x here, so let's go ahead and replace it in there. So mi xi squared. Just to keep things clean here. So I have two terms because I have two masses. And I said we should calculate the moment of inertia about the center of mass. We can calculate the moment of inertia about other points and we will get different answers. Okay? And what that means is that is the moment of inertia if you were to rotate that object about the point that you're calculating the moment of inertia from. So we are going to calculate the moment of inertia about the center of mass, and so I will subscript moment of inertia about the center of mass, so ICM. There are methods of calculating the moment of inertia about another point using what's called, for example, the parallel axis theorem. If we wanted to rotate this object about another axis due to some torques about that axis, and we could calculate that as well. But let's stick with just the center of mass case first to keep things a little bit simple. We're going to have two terms here. So M1, this is the center of mass right here. So M1 is a distance of 2/3 L. So 2/3 L, 2/3 L squared. Oh, M1 is 1 kilogram, right? M1 is 1 kilogram. Let's go ahead and fill that in. So that's going to be 1 plus, oh my goodness, my mouse is really giving me trouble. Okay, and then times, plus 2 kilograms times, what's the distance from the center of mass for 2 kilogram mass on the right-hand side? It's 1/3 L. So 1/3 L here. There it is. We have to square those. So what we end up with, 4 over 9 L squared plus 2 times 1/9, right? So 2 over 9 L squared. And so this comes out to 6/9 or 2/3 L squared. Okay, so this is the moment of inertia of this kind of stick with two masses on the end, and the stick in between the two masses is very light, so it doesn't factor into the moment of inertia calculation. So it's like two masses connected by a massless rod. Okay, so if we gave a length now for L, if we said, okay, let's let L be 1 meter, then we could calculate a numerical value here. So if we let L be 1 meter, 1 meter squared is 1, right? So we'd end up with, if we want to put a decimal value here, it'd be 0.667 kilogram meter squared. Okay. Now, what would happen if we were to increase the masses of these two balls on the end? What if we were to double the mass of each of these balls so that the center of mass stays in the same location, but we've increased the overall amount of mass that we have in our problem here? What would happen? Well, we'd take a look here. We would take a look here at these masses in the summation formula. And we would say, okay, if we double all of the masses, then we would just pick up a factor of 2 here, right? If we doubled all of the masses, we would just have these factors of 2 out in front. And so what that means is, if we doubled up the masses, if we made this one a 2 kilogram, and we made this one a 4 kilogram, as long as we double both of them, the location of the center of mass doesn't change. If we double one of them, it would change. As long as we double both of them, then the moment of inertia would increase by a factor of 2. Okay, so if we were to double the masses, so doubling the masses here, double the masses means we get double the moment of inertia. Okay, it's directly proportional to the mass, right? Directly proportional to the masses of what you have in the system. Now, if you were to double one of those masses, well, then you've changed the game a little bit. You've altered the moment of inertia in a way that we can calculate, but it's a little bit less predictable than just doubling it. We'd have to go back and we'd have to calculate again what the moment of inertia is. Okay, so now let's go ahead and take a look at some common shapes that we might come across. Now, I mentioned before, and the formula is still there, that this expression for the sum of all of the masses times their distance squared from the center of mass, I mentioned before that we can have a situation in which we have a continuous distribution of mass. So for example, I could have a rod like so, and the rod is obviously full of a bunch of different masses, right? A bunch of atoms make up the rod, but we would treat that as a continuous system. and we would change this summation to an integration. And so we won't do that because obviously we want to do the things without calculus in this class. But you could also have a disk, right? A disk has all this mass in the middle. You could have a ring. A ring has only mass on the outer part of the circle there, right? So you could have a ring like so. And you could, of course, have a sphere as well, right? So here's a sphere, right? And so we have, mass all over inside the sphere. And there are moments of inertia for all of these common shapes, okay? And we're not going to go through the process of deriving them because that requires calculus. But let's go ahead and write some of the ones down that are kind of common. And I'm just going to copy these formulas from the textbook here. I have the little table open over here on the side. If you have a point mass, suppose, for example, you have a pendulum like so, and this is just a mass on a string, and the string is massless, okay? And this thing is free to rotate about this, this point up here at the top. The moment of inertia of this point mass here rotating about this point here. So rotate, this is the rotation point here, or the rotation axis. So if this is the rotation axis here, then the moment of inertia for this point mass is mr squared, if this distance here is r. The length of that string is r, okay? Now that's if you have a point mass, so that would be like, like if you had a yo-yo, okay? If you like let a yo-yo go down and then you start spinning it around in a circle, okay? The moment of inertia for that system, for that point mass rotating about your hand, if you're spinning it around your hand, right, is mr squared. It's a simple formula. If you have a ring like this, whoops, if you have a ring which has some mass here, because all of the mass is the same amount of distance from the center, if we're rotating about the center here, so now this is the axis of rotation here, or the rotation axis, of, you guys can read this, right? Of rotation. Can you guys read this? Axis of rotation. Okay, axis of rotation there. If the axis of rotation is coming out there through the center of the ring there, then all of the mass is a distance r away from that central axis of rotation. And so the moment of inertia now about the center of mass through the axis of symmetry. Now you can see why moments of inertia can get a little bit complicated. So through the center of mass, through the axis of symmetry, is also equal to mr squared. And now the meaning of m is the total mass of the ring. This formula is actually easy to derive. This formula boils down to I equals sum of mi times ri squared, but all of the r sub i's are the same, and so the summation simply becomes this times r squared, which is equal to the total mass times r squared. So that formula we can derive pretty simply, right? Now things start to get complicated. Disk. A disk has mass everywhere inside of it, and so the distances from the center of mass to each individual atom, let's say, in the disk, all those distances are different. And so this is one where you need to use calculus. But we can just write down the formula. As long as we're rotating through the center of mass, which is right in the middle here if it's a uniform distribution of mass. So if it's a uniform disk, the center of mass is right there. By the way, the center of mass for the ring here is that central point. We put it in red there. So the center of mass can be a location where there actually is no mass. Then the center of mass here for the disk, I believe is 1/2, and let me double check that. So it's 1/2 mr squared. And again, r is the total radius. Let me use another color. R is the outer radius here of the disk. So it's a nice expression because we don't have all these different radii that we have to keep track of. It turns out we can write the answer in terms of the actual just radius of the disk. So let me double check that that answer. Yeah, that is correct there. Okay, and then let's go ahead and take a look at one more kind of bizarre one here. Actually, let's take a look at 3 more, actually. Now that I think about it, there's actually a really nice thing that we should take a look at here related to the rods. But if we have a sphere, again, if it's a uniformly distributed sphere, there's mass everywhere on the inside of this thing, right? But as long as we're rotating the sphere through the center of mass, which is the center of the sphere, if it's a uniform sphere, it doesn't matter what way we rotate the sphere because it's a sphere, right? It has spherical symmetry, so we can rotate it in any axis we want as long as it's through the center. That would be 2/5 mr squared. Okay. Now here's an interesting thing, and this really highlights that the center of mass is much different depending on where you calculate it from. So suppose for a second that we have a rod, and this rod lies on the positive x-axis, like so. The length of the rod we can take to be L. Let's actually take it to be R. Or no, what do they use in the book actually? They use L. They use L, let's use L. Okay, the length of the rod is L. If I were to rotate this rod in this direction here, so it comes around over here, back around like this, and so forth, and obviously this is from this point here, this is not rotating the rod about its center of mass. This is rotating the rod about some point, on the edge of the rod. You can calculate the moment of inertia for that situation, and it turns out, I'll write moment of inertia about the end, if I can write it, end of rod. It turns out to be 1/2 ml squared. Let me double check that. Excuse me, not 1/2, 1/3. 1/3. Okay, 1/3 ml squared. Again, these formulas will be given to you on the test. I wouldn't ask you to remember all these moment of inertia formulas. So if I ask you to do a question with a particular kind of shape, I'll give you the formula for that shape, okay? So don't worry about that. You don't have to go and memorize these formulas. The moment of inertia rotating the rod about its endpoint is 1/3 ml squared. How about rotating the rod about its center of mass? So now the rod is here. So this is L/2, and this is L/2. So the total length of the rod, again, is L. The center of mass now is smack dab in the middle of this rod. Again, if it's a uniform rod, which everything is going to be uniform in this class. Otherwise, we need calculus. The moment of inertia now to rotate the rod about its center of mass in this direction again, the same direction, so we're rotating it in the same direction, is 1/12 ml squared. This one I actually always remember because it's so unique. It has the factor of 1/12. But again, I'll give it to you if I want you to calculate something with it. Now, this highlights the challenge, so to speak, of rotating objects about a point that is not their center of mass. 1/12 ml squared is much smaller than 1/3 ml squared by a factor of 4. Okay, so rotating about the end of the rod is bigger than rotating it about its center of mass. That's a very key takeaway from what we're doing, is that rotating about different points gives different moments of inertia, which makes it easier or harder to rotate those objects. Okay, so it's going to be much easier to rotate this one about its center of mass. So easier. Can you guys read what I'm writing? Easier to rotate. Oh, I hate this mouse. I need to just go get a new mouse.
It's okay. You're saying it as you write, so I think it's fine.
Easier, well, thank you. Easier to rotate. So it's easier to rotate about the center of mass. That's the whole point here. Is that always true? Is it always true? It's always going to be easier to rotate about the center of mass? The answer is yes, if the object has a uniform mass distribution. Always true if the object has a uniform mass distribution. In other words, constant density. If it doesn't have constant density, then there are definitely some situations where rotating the object about another point would be easier. Okay. All right, there's one more really important concept that we just have to cover. Actually, there's two. We just have to cover them. I don't want to leave you guys, without actually covering these two topics, because trying to figure it out on your own is going to probably be pretty difficult. And that is rotational kinetic energy, which will be really easy to derive for us real quick. If I can write it, rotational kinetic energy. This one just falls into our laps nice and easy. Rotational kinetic energy. Start with translational kinetic energy, 1/2 mv squared. Well, we can replace, if we have an object which is rotating, we can replace the velocity with omega, or rather r times omega. We square that. So that's going to be 1/2 mr squared times omega squared. And you guessed it, that mr squared term is the moment of inertia. Okay. If we have an object like a bicycle, which is moving, it has a translational motion, and it has wheels that are rotating, then that object has both translational kinetic energy and rotational kinetic energy. So the total kinetic energy should always be the sum of those two. So the total kinetic energy is going to be the kinetic energy of translation plus the kinetic energy of rotation. Right? So got to make sure that you include both of those terms. So for example, for a bicycle, we would have 1/2 the total mass of the bicycle times its velocity squared plus 1/2 the mass of the wheels times the radius of the wheels squared. And let me see, did I use the right formula there? I can't remember. So I come back up here, I scroll up. Where is a ring? And yes, I did use the correct formula. A ring has a moment of inertia mr squared. So scroll back down here. So this is the moment of inertia of the wheel, which is equal to the moment of inertia of a ring. Because it's really that rubber and metal on the end of the ring, or on the end of the tire, I mean, that contributes to the moment of inertia the most. And then the spokes of the wheel, those are almost massless compared to the rest of the wheel. And then I forgot the omega squared there, but omega squared is the same as oh wait, no, we already took care of that. No, we're done here. We're done here. So the kinetic energy of a bicycle, for example, might look like this. And we probably could be really careful here, and we could note that this velocity here, since we're talking about rigid bodies, we could be careful here and make sure that we indicate that the velocity that goes into calculating the kinetic energy should be the velocity of the center of mass, right? Because that mass is moving together as if it were a point mass with all of the mass concentrated at the center of mass. Now you could combine these two terms, and that was kind of what I was getting at a second ago, but let me just not do that. Let me just leave that there. You can combine these, but we're just going to leave it here at this because this is good enough for what I'm pointing out. And let me give you an example of how we apply these. Well, let me tell you where to look in the book. So page 213, do example 8-12. Okay. So do this example here for your own practice. And here's what I would do. Ask yourself the following question. Let me just type it out, and you guys just write this in your notes, and then when you do that example, you can what about a cylinder? So the problem, this example 8-12, what you're doing is you're taking a look at a sphere rolling down an inclined plane. Okay. If you have a sphere rolling down an inclined plane, well, it's moving down the plane, right? But it's also rotating. So it has translational kinetic energy, it has rotational kinetic energy, and it has gravitational potential energy. And you can write down an expression for the total energy. And of course, energy has to be conserved, right? And you can calculate the velocity of that sphere when it reaches the final, the edge of the incline. And so my question here is, well, what about a cylinder? So repeat the same analysis for a cylinder. So for a cylinder rolling down an inclined plane, what you can do is you can actually calculate, you can actually determine in many different cases, and not just a sphere and a cylinder, but for other shapes as well. Like if you have, if you had like a hoop, or if you had like a disc, and you just roll all of these objects down an inclined plane, you can actually determine, independent of their mass, independent of their size, which of those objects will actually make it to the bottom of the incline first. And it all has to do with their moments of inertia. So I'll leave that maybe as a follow-up question. Which shape would win the race down the incline? That's a really important question. And actually, this is a question that's addressed in the following example, so 8-13. But it's a conceptual question. There's no calculation. You can actually do the calculations if you want to. Okay. And then we really need to cover angular momentum before we quit here. I know we're a little bit over, but we definitely need to do it. So let's take a look at it now. So angular momentum. Again, torque and angular momentum are vectors. I'll let you read in the book how to determine the direction of those vectors. It's something called the right-hand rule or the right-hand corkscrew rule, something along those lines. I'll let you guys investigate on your own how to determine the direction for that. Now, if we proceed how we did with force, force we saw was change in momentum over change in time. And we saw that if there was no net external force on a system, then momentum was conserved. Exactly the same thing is going to be true for torque. We're going to let torque be equal to the change in angular momentum, which we use the letter L for, which probably adds to the difficulty for students learning. Angular momentum has the symbol L. So angular momentum here. Angular momentum, here it is, divided by delta t, so the same kind of thing. And if you want to, you can define an angular impulse, and that's not something that's a very common language that you see, angular impulse, but you can do it. If you multiply the delta t over and you can say delta L is angular impulse. Everything, all of the analysis follows from this here, this definition here. So angular momentum is going to be like momentum, but related to rotational motion. So let's go ahead and take this equation here and rewrite it as I times alpha. Remember, the torque, the net torque on a system is moment of inertia of the system times alpha. And then what we can do is we can replace alpha with its definition, which is delta omega divided by delta t. Right? And if the moment of inertia is not changing, well, it's never changing for a rigid body, then we can bring the I inside of the delta. So we can say delta I times omega divided by delta t. And this gives us our definition for angular momentum. So delta L equals delta I omega, or L equals I times omega. Okay. So there it is. That is what we mean by angular momentum. Now we could substitute in I for a sphere, I for a disk, right? I for a point mass, and calculate the angular momentum for those different situations. One other important formula that I will actually point out is that the angular momentum can be written as R times P for a situation where we have circular motion. So circular motion. It's actually a little bit more general than that, but if we want to go outside of circular motion, we have to use a radial vector and the momentum vector. And so that's going to complicate things a little bit. So we could replace P with M times V. And then we have a nice little formula for the angular momentum in terms of the mass, the radius of the motion, and the velocity. Now, the other thing is that if the torque is 0, if the net torque is 0, you probably guessed it already. If the net torque is 0, that means the change in angular momentum is 0. That is a new conservation law, conservation of angular momentum. If the angular momentum doesn't change, then that means it's conserved. It's the same value all the time. So conservation of angular momentum. Put a box around that one. Very important that angular momentum is conserved. This applies to a whole lot of situations, actually, conservation of angular momentum. For example, think about the Earth and the Sun. Angular momentum is going to be conserved in that case. Let me show you why. If I take, where's my mouse at? There it is, okay. If I take the Sun, let me use like yellow here. If I look at the force between the Sun and the Earth, Earth is the blue planet here, so let's get a blue ball over here. The force between these two objects is a central force, right? It's a force that acts between the centers of mass of these two bodies, the Sun and the Earth. So there is not going to be a lever arm to generate a torque on this system. So these forces here, the force of gravity is parallel to the lever arm. That means that the net torque is 0. And therefore, angular momentum is a constant. It's conserved. So delta L is 0. Okay. So that's really nice. That helps out a lot in the analysis of like the orbits of the planets and stuff like that. There's another kind of really nice thing I would invite you guys to try for yourself, and maybe I can show you guys right now as like a short little demonstration, but it has to do with this equation right here. The angular momentum is the moment of inertia times the angular velocity. And I will go ahead and pull up a video to show you guys that. Okay, and here I have the video. Okay, and let me maybe bring it over here. And I'm going to stop sharing this screen now, and I will share YouTube. Can everybody see the video when I full screen it? Can you guys see it? Okay, so the idea is angular momentum is moment of inertia times angular velocity. So what do ice skaters do? They usually start with their arms really far apart, right? And then if they want to speed up, they bring their arms in, or they start with their leg really far away from them and they bring their leg in, and it helps them spin faster. The reason is because of conservation of angular momentum. When you have your arms out, your moment of inertia is big because your arms can go really far away from your center. As you bring your arms in, you change your moment of inertia. You make it smaller. And if your moment of inertia gets smaller, your angular velocity has to get bigger. Okay? And so that's a principle that ice skaters use to increase their angular velocity. So let's see.
For decades, the Winter Olympic Games has drawn people from across the world to marvel at breathtaking athletics on the snow and ice. One of the most popular events is figure skating. Athletes meld acrobatics, dance, and physics into mesmerizing performances. It is the sheer precision that separates the skilled athlete from the novice. Through years of tireless training, skaters must learn to understand and use angular momentum to become the best in their sport. Angular momentum is the product of a skater's moment of inertia and angular velocity, and is represented by the letter L. When a skater is rotating with no net external torque acting on her, angular momentum is conserved. With her arms and leg outward, she increases her moment of inertia, which reduces her angular velocity. As she pulls her arms and leg inward, she is able to spin faster since her angular velocity increases while her moment of inertia decreases. And this is how skaters become champions.
Okay, so that is a very kind of interesting application there for angular momentum. Now let me go ahead and go back to...
You've seen the title, so you know this is leading to a
there's
certain
another,
fractal.
hold on a second, there's another
Actually,
video
it's an
playing.
infinite family of fractal.
Oops. Okay. So let's go back here for a second. That's pretty much what we needed to cover there. I know we weren't able to get to too many examples there for those last couple topics, but what we can do here is we can just answer any questions we might have about any of those topics. So I'll go ahead and we'll say that, okay, now we're done lecturing, but if there's any questions, now we can just answer questions. So you guys let me know what you want to do. Do you guys have questions? Is that good? So I'm okay to keep going, and we could do some more examples if you guys want, or if you want to see something specific.
I think just a quick one. I don't know if I'm thinking too hard into it, but for the rotational kinetic energy, when you were giving us the example of the bicycle and the total kinetic energy, if it was like a car tire, would that be considered like a disc because it's heavier, or is that still like a ring shape?
Yeah, so that's a good point. Maybe a car tire would be a little bit more like a disc because there's a lot more metal
Mhm.
in the inner region than a bicycle tire. So that's something that when a problem is posed to you, the person who creates the question has to let you know, okay, treat the car tire as a disc,
Mhm.
not a ring. Yeah.
Okay.
And I mean, that's also an example of maybe where it's not really a uniform mass distribution. The density isn't constant, right? Because you're going from metal in the middle to like rubber on the outside. When you have a situation like that, what you can do is sum the moments of inertia. So let me go ahead and maybe write that down. So if you have a situation where we have maybe something like this, where this part here is some material and this part here is some other material, the total center of mass for this, sorry, the total moment of inertia is the sum of the moments of inertia of the two individual pieces. So this might be the sum of a ring and a disc. If I can write, there we go, plus that there. Okay, so that's how you would adjust for some shape that's maybe comprised of two different pieces. So you might treat the tire on the outside as a ring, and then you might treat the metal on the inside, the inner part of the tire, as a disc, something like that. And you just sum them up. And you can do that only because you're rotating about the same point there. Both the center of masses are aligned perfectly there, and so you can just add those to get the correct answer. Are there any other questions?
I have a question that's unrelated to this chapter, but related to the test.
Okay.
In a previous email, you mentioned wanting to have like a study session for the calculus students to go over like the calculus we would need for the test.
Yeah.
When would that be?
We could probably do that right after the other session,
Okay.
if that works. Is that
Yeah, that's fine with
okay?
me.
Are there any other 210 students here still? Okay, maybe maybe not, but yeah, we'll just do that like maybe right after the other session. It's not going to be a lot. It's not going to add on like another hour or 2 hours. It's probably like a half an hour, and I'll talk specifically about some type of problem that I'm going to give you where you'll have to do some calculus, and it's not going to be a lot.
Okay, thank you.
Any other questions about the test though?
It's going to be similar to last time where we have to bring the formulas to the table, right? On the occasion that you give us like one formula in a problem.
Yeah, any problem which requires use of like a specialized formula, like tailored to a specific setup, like for example one of these moment of inertia problems, I'll just give you the formula.
Okay, but
It'll
the
just
general
probably
one.
just be included right there, either on the front page of the test with some of the constants and things, or in the question itself.
Okay, thank you. Oh, and then do you know when we're gonna potentially do the study session on Saturday?
Well, I'll send out an email and you guys can give me feedback on that, but it'll be recorded and posted. So
Okay,
even if it happens to be at a time where some people can't show up, I'll record it.
okay, thank you.
This next test, by the way, will be it will be multiple choice plus like maybe 2 free response questions, something like that. Just because some people want some partial credit, that kind of thing. So I can do it that way. I actually just finished writing my test for my other class. I think I had 3 free response questions actually. My experience tells me though that it doesn't make a difference. I've given all free response before, all multiple choice. Giving a mix, like, it usually doesn't matter. You either know stuff or you don't know stuff. You might know a little bit about something, but yeah, just in my experience, and I've talked to other faculty about it too, like, it really doesn't matter if you give multiple choice or free response. Tends to, the distribution of grades tends to be the same no matter what. Any other questions? Does anybody want to see a particular example? All right, well, if there aren't any other questions, feel free to leave the meeting. I'll stop the recording now. How many questions will it be? Well, I haven't written it yet, so I don't know. I'll try to make it an hour and a half.